Thank you. It's a great pleasure to be here. I did have to travel a long way. I've been to lots of these conferences. I was at the first one, organised 3 of them, I think numbers 3, 5 and 11. So when I say I thank the organisers or I salute the organisers, I really mean that. I know how hard it is to do. And in those days it was only a few people, 20 people perhaps, and this is an enormous conference, so many congratulations to the organisers for doing so well with that. One little detail, it seems to be sorry, just want a laser.
No, it's just I can
turn it the other way. Turn it over. I'm now at Curtin University, which is another university in the same city. I think I'm listed on the program as University of Western Australia, but now I'm at Curtin. So this is joint work with my collaborator Gopal Nair, who is at the University of Western Australia, and I'll mention some other people along the way. So the starting point is, for many purposes in spatial statistics and other fields, we use Gibbs point processes. And there's a problem with that because many of the important properties of such a process are not known as an explicit function of the parameters. For example, the intensity, the average number of points per unit area, and the second order properties like the pair correlation function are not given explicitly as functions of the model parameters. So imagine, you're going back to school and you're learning a new branch of statistics, and the lecturer says, well, here is the distribution which we're going to use to study for most purposes. It's like the normal distribution in this field. It's the most important distribution. And we're going to use it all the time, but we don't know its mean. That's just really uncomfortable. So, of course, there are approximations, many approximations, but they have their limitations. So here's an example, which I'll come back to later on. This is for a Gibbs model called the Strauss process. And when it has a interaction parameter called gamma, and when gamma is 1, the process is a Poisson process, and when gamma is 0, it's a hardcore process of a certain kind. And the so-called exact values I got by exhaustive simulation, 100,000 realizations. So they're pretty reliable. And this is the very popular mean field approximation. So the mean field approximation when gamma equals 0 is the intensity is 0. So that what happens is when you get close to a hardcore process, the mean field approximation breaks down and cannot even be used for qualitative purposes. So that's difficult. Okay. Well, so this intractability is a major obstacle, and in fact was one of the major reasons why Markov chain Monte Carlo started in the first place. And I've been thinking about this for a very long time, but I was really forced to do something when I started developing software, and in particular software that got put into a book. And you can't have a blank page where it says the mean value is unknown in a book. That's embarrassing, so we had to do something about it. So here's the kind of thing that you can do with existing software. Here's an example data set, which looks like these are trees, positions of trees. It looks like the trees don't interpenetrate, they stay away from each other a little bit. A Gibbs model is appropriate. You can easily, in this package, you can fit a model. This is how you fit a model with a Strauss interaction. You can read off the fitted parameters of the model very easily, and you can simulate the fitted model. You can do all kinds of things, but you can't figure out the intensity of the fitted model. So here's the sort of context I want to attack. We have some Gibbs point process, and to make things simple, I'll assume that this is a stationary point process, just to make life easier for us in the talk. The thing we're really interested in is the intensity, so that's the expected number of points per unit area. And there's a conditional intensity, which is another quantity that can be evaluated at any location. Sorry, I put 0 there when I should have put an arbitrary point u, say. So at any point of space, you can ask what's the conditional probability that there will be a point of the process here given the rest of the entire process. That's the conditional intensity. So usually what happens is that the conditional intensity is known or even written down as a description of the model. So the conditional intensity is known explicitly as a function of the parameters of the model, whereas lambda is not. Lambda is just a property of the model, which we don't know, the average of the distribution. And the only available means to get at this in general is a consequence, well, this is really just a consequence of the law of total probability, right? This is a kind of conditional mean. The expectation of the conditional mean is the unconditional mean, so the law of total probability. But in this context, it comes from the Georgi-Wing-Zesin formula. But there you have it, and that's probably maybe we should either memorize that or I should write it down somewhere. We're going to need that. Well, I've put 0 here, that's just the origin, but we could have any reference point, of course, any fixed point. And the problem is that this is an unknown equals unknown. Although this quantity, the conditional intensity, capital lambda, is known explicitly as a function of the parameters and as a function of the realization of the process, this expectation is intractable because it's in expectation with respect to the distribution of the point process we're trying to study. Right. So, example, a pairwise interaction process is one in which this conditional intensity thing is, well, first there's a constant sort of term, then there's a contribution from each point. Now what I mean here is xi is one of the points of the process. We take a product over all points of the process of a contribution that depends on the vector difference between the existing point and the query point u. So u is just some point in space, like the origin, and I consider this function of the vector difference between a point of the process and the query point. And g is just a function called the interaction function. And so this equation here just becomes something in which, again, the right-hand side is not known explicitly. Even if g is given to us explicitly, we don't know this expectation of this potentially infinite product. That's really the probability generating functional of the point process and is generally intractable. But you can, here's the key idea is to think of this as some kind of self-consistency property. You know, these are two properties of the distribution of x that are related or equivalent. Special case of a special case is the Strauss process, where the interaction term is 1 if the distance is greater than a certain threshold r, and otherwise it's a value gamma, where gamma is the so-called interaction parameter, which is between 0 and 1. So then, so here, for example, are pictures of the realizations of the Strauss process with different values of gamma. On the right is gamma equals 1 is equivalent to a Poisson process. On the left, gamma equals 0 gives you some kind of hardcore process. And actually, I've done a trick here because I've used the answer. So I fast-forwarded to the end of the talk, got the answer, came back, and constructed these simulations so they all have the same intensity. Now, you can't actually do that until you've solved this problem. So this picture doesn't exist. Forget this picture. It doesn't exist until we've solved this problem, okay? Right, but there they are, and you get the idea. Gamma is a measure of the strength of interaction. So the conditional intensity for the Strauss process basically just involves counting how many neighbours there are, how many nearby points there are to the query point u. And you get something like this, which is getting even simpler, but again, it's a probability generating function under the distribution of the point process. So we keep coming back to the fact that it's a kind of self-consistency relation where both sides of the equation involve the distribution of the process. We don't like that, so let's make that go away. Oh, sorry, just one more slide. Of course, you can prove all kinds of nice things. You know, many properties can be proved just by knowing this. You can prove it's an increasing function of gamma, or it's a continuous function, and all kinds of other things. But okay, here's the idea. Let's just wish the problem away, right? So on the right-hand side, I'm just going to replace that x by a Poisson process with the same unknown intensity lambda as the point process x. Right? So that will give me instead an equation like this. So if capital pi lambda is the Poisson process with intensity lambda, what I'm doing is this lambda is the same as that one. So it's unknown, it's on both sides of the equation. You all see that? So in other words, we're going to solve the equation lambda equals m of lambda, where m of lambda is the expected value of the conditional intensity of our interesting point process, our Gibbs process, when it's evaluated for a Poisson process with intensity lambda. So the solution, if it exists, we call it the Poisson-saddlepoint approximation. That's a pretty grandiose name. We don't really know what else to call it. And that name comes from this, this paper. Other people were involved in this idea. It's now too difficult to figure out how it came about. Uta Hahn at the back, hiding at the back there, was involved somehow. And I remember asking Stoyan about this once, so I'm really unsure exactly who came up with the idea. The more surprising thing is that we can't find anywhere in the the statistics literature or the statistical physics literature where this is laid out very straightforwardly, so we're not sure why that might be. Anyway, so let's just try this out, try out this method for an example. So for the case of a stationary pairwise interaction process, remember that's the one where the conditional intensity involves a contribution from each point, existing point in the process. Then what you're asking, sorry, I'll switch notation here. That means the expectation for a Poisson process with intensity lambda of this product. And that's straightforward for a Poisson point process. You can figure out that it's just something to do with integrating g minus 1 or 1 minus g. So when g equals 1, there's no interaction. So 1 minus g is a measure of the amount of interaction. So this capital J, sorry, I'm thinking that's French. This is J in French and G in English. Isn't that crazy? Anyway, here we are. This is G. Capital G is the integral of the pairwise interaction. And assuming that is finite, it's called the second minor cluster integral in statistical physics. And the solution to this equation, the bottom equation, is this equation here reduces to that. And the solution is simply to find the inverse function. If you find the inverse function of the function x e to the x, that's the Lambert's W function, and so you can write down an explicit form for this approximate intensity as a function of two things, the first order term beta, first order parameter beta, and this quantity g, which is determined by the interaction. So later on, somebody did find something in statistical physics called the Poisson-Boltzmann-Emden approximation or equation, which is equivalent to this. So I'm not sure, I may well be just recapitulating something that a statistical physicist did in the 1920s, but I wish we had known about that decades ago. We would have been able to do lots of other stuff. So here's how it works for so here it is calculated for the Strauss process. So the plus signs are the true values, the dashes are the mean field approximation which I mentioned, and the straight line is the solid curve is the Poisson-saddlepoint approximation. So I would call that a pretty good approximation. It's good enough to use for practical purposes, the practical purposes that we need. So I just want to point out it's not the same as approximating the process by a Poisson process. rather, what we're doing is we're approximating a functional of the Gibbs process by a tilted version of another functional of the Poisson process. So it's a kind of tilting approximation. It's qualitatively similar to the saddle point approximation in classical statistics from my strange jet-lagged viewpoint. So that's why we call it the Poisson-saddlepoint approximation. It's the mean field approximation, the one that doesn't really work, which is associated with a Poisson point process approximation. So if you say, let's find the value of lambda which minimizes the Kullback-Leibler divergence between the Poisson process and the target process, that selects a value of lambda, which is the mean field approximation, which doesn't work. And if you think about it, that makes sense. Consider a hardcore process. The Poisson process, which is most similar to a hardcore process, is empty. So that's why the mean field approximation to the intensity of a hardcore process is 0. Okay, maybe that's not obvious. Okay, so I'm happy with an approximation without any theory, as long as it works in 2 cases. But Dominic Schumacher and Kaspar Stucki, where is he? He's hiding. Looked into this more rigorously, and they actually proved some bounds that are satisfied. So if we're still in the pairwise interaction process context, then they actually proved some rather tight bounds which the intensity lambda must satisfy. And what they're doing here is examining properties of the probability generating functional of the process. And it turns out that the Poisson-saddlepoint approximation also satisfies the same bounds. So there's a set of limits between which the true answer and the approximation must both lie. So that means you have error bounds. And here are the error bounds for this example of the Strauss process. So the grey colour there is the bounds for the bounds for both the true intensity and the Poisson-saddlepoint approximate intensity. And so it's relatively easy to code that up. So now you can, for example, just, if you have fitted a model in this package SPAT-stat, you can just say intensity of fit and it spits out a number, which is fine. However, this only works for pairwise interaction processes. And many of the things that we deal with in applications involve interactions between multiple points, more than pairs of points at a time. And so what do we do in that case? So let's just consider a general Gibbs point process model, and it depends on some parameter theta, and the conditional intensity also then depends on this parameter theta, and we define m of lambda. Now m of lambda comma theta is the expected value of the conditional intensity for a Poisson process of some given intensity lambda. And then we're trying to solve this equation again. So it's the same technique to be applied. And it helps if you can prove that the conditional intensity is increasing with respect to the point pattern. So if you add more points, you get, let's say, for example, a higher conditional intensity. It could be monotone increasing or monotone decreasing, and if that's true, then you can prove that this function m is also monotone, increasing or decreasing, and then you can use that to prove that the Poisson-saddlepoint approximation exists, because you're solving an equation which is going to have a solution. So to get further, let's suppose that the conditional intensity has finite range, so that it only depends on the points of the process within a finite distance away. And that means, so then this thing x intersected with a ball of radius r centered at the origin is a finite point process, and now we can just consider the number of points as a random variable and get somewhere. So then we get a simple, this is the simple expansion of this function m by conditioning on the number of points. It's going to get a little bit ugly for a while, but I promise you there's something really interesting coming up. So what happens here is that we have a Poisson number of points with mean equal to the expected number of points in disk of radius r. And we consider for each n a binomial point process, so n independent uniformly distributed points in the disk of radius r, and then we just evaluate the mean we just evaluate the mean of the conditional intensity for that process. Okay, so we've got some kind of simple series expansion, and in principle we only have to evaluate these terms here. Okay, so now comes every possible trick in the book will now be used. The first one is we'll use scaling properties so we don't have to worry about the interaction range. We'll rescale the process so the interaction range is 1. Then we will figure out some way for small n. We will either evaluate, for n equals 0, we'll probably evaluate the answer exactly, and then maybe for n equals 1, and then for a few small values of n, we'll compute this term accurately, perhaps by intensive simulation. We only have to do that once and for all. So go to your administrator, get a large amount of supercomputer time, and go away and evaluate this quantity once. But then it's an infinite series, and the tail behavior of the series, the behavior of the series is going to depend also on the terms for large n. So we are also going to have to figure out something related to the limiting behavior as n goes to infinity. So there is a stochastic geometry problem in there. What happens to the conditional intensity when you have a large number of points in the neighbourhood of the target point? And that's going to involve a limit theorem. Okay, so then we will combine these results to compute this target function m approximately, and then we'll solve the equation to get this approximation. That sounds hopeful. But to just spell it out a little bit further, so suppose the conditional intensity is a log linear function of the parameters theta, then what you're dealing with is the moment generating function of this statistic t. So ultimately what we're going to have to do is figure out the asymptotics of the moment generating function, or equivalent, the asymptotics of the distribution of this statistic t, whatever that is, when you have a large number of points in a disk of radius 1. So the strategy is, first of all, for some n, say 20, I'm going to use extensive simulation, for example, to tabulate the cumulative distribution function of the statistic t. Then I'm going to ransack the library looking for theorems that tell me about the asymptotic behavior of the same statistic when n is large, and then I'm going to combine those to get an approximation to the moment generating function. So let's take an example, my favourite, the area interaction process, or the Widom-Rawlinson penetrable sphere model. And that's where the conditional intensity depends on this quantity c, which is the area. So the modulus sign means area of the intersection between a ball of radius r, centred at the query point, and balls of radius r centred at all the data points, all the points of the process. Here's a picture of that. So what I'm saying is that this shaded area here is the statistic t in question. Okay? So I have a model in which the conditional intensity is e to the theta times that area. I can draw simulated pictures of this process. So eta is log theta. So eta is the thing which is exponentiated to get the density. And when eta is equal to 1, you get a Poisson process. When eta is greater than 1, you have a kind of clustered behavior. And when eta is less than 1, you have repulsive behavior. So we can easily prove that this is monotone in X, so that the solution exists. There is a Poisson-saddlepoint approximation. And for the series expansion, we need to figure out basically the moment generating function, equivalently the uncovered area. So I'm going to work with the uncovered area. So imagine, take a disk of radius 2, put n independent random points in the disk of radius 2, draw a disk of radius 1 around each of those points, and then find out how much of the area in the disk of radius 1 is not covered by these circles. So that shaded area there is the statistic I'm going to study. First stage, go back to the supercomputer and get tabulated estimates of the cumulative distribution function of AN. So this is A1, A2, A3, etc., up to A25. So those are, you can take them, they're pretty accurate estimates of the cumulative distribution functions of the random variables A sub n, the uncovered areas, when you put 1 point, 2 points, 3 points, etc. In this region. Step 2, asymptotics. Right, so now we need to consider a large number of random disks placed so that they intersect a disk of radius 1 and figure out how much area is uncovered asymptotically. So rescale and normal kind of asymptotic theory. Fortunately, that has been done by 2 Australians. So the late Peter Hall and Roger Miles, R.E. Miles, both worked on related problems, so I'll just go through some of their results. So Peter Hall wrote a book about coverage processes dated 1988, and some of the marvellous results in there include approximations to, so this is the coverage probability. That's a probability that there is no uncovered area, probability that the balls completely cover the unit disk. And the covered area is very close to 1 when n is large, and this is a good approximation. Then there's a separate question about the expected area given that it's not 0. So the expected area that is uncovered given that it's not 0. And that also has a nice asymptotic expression. For our purposes, we also would like this to work for small n, so I've actually tweaked that by replacing n by n plus 3. So that's asymptotically equivalent, okay? It's not cheating. It is cheating, but it works. So it's not cheating. So I think the black circles are the correct answer, the probability of complete coverage. The white circles are the approximation I'm going to use. Then there's a really beautiful result proved by Peter Hall. Imagine, this is a Boolean model, so imagine a Poisson-point process. Around at the center, at each point of the process, place a disk of radius 1 and take the union of those disks. That's the grey area that you see there. Can you see that at the back? Sorry, the lighting is on tilt. So now Peter Hall was interested in the so-called chinks, C-H-I-N-K, chinks, which are the gaps between the white gaps which are not covered. So imagine a forest, rainforest perhaps, lots of tree canopy above, and very occasionally the bright sun shines through a small hole in the canopy. That's what we're looking at here. As the canopy becomes more and more dense, the chinks, the holes, become smaller and smaller, and Peter Hall proved that asymptotically they become equivalent to the polygons of a Poisson line tessellation. You can imagine why that happens. When there's a lot of disks, the chinks are very small. So the curvature of these disks doesn't matter anymore. They're very small, so they're effectively, the boundaries are effectively straight lines. It must be a Poisson line tessellation. Obvious. It's a bit more complicated than that, but anyway, it's a very beautiful fact that asymptotically you can see a few small ones there, and the distribution of these, the size distribution is explained by the approximation that we described before, and the shape distribution is that of the cells in the Poisson line tessellation. I think it's a lovely result. Anyway, Roger Miles, the second picture, figured out that the area of a typical polygon in the Poisson line tessellation has a particular variance to squared mean ratio. So we can now put this all together. So this is the conditional distribution of the ANs that I showed you before. Let's look at AN, come back, AN divided by its mean. So I'm actually rescaling these quantities so that they have mean 1. Or actually, I'm using the approximation, so they don't quite have mean 1. And there are some very fine grey curves there, which are the results for n equals 1 to 25. And then there's about another 25 black curves there, which are for n equals 25 to 50, suggesting, that's not a proof, but it's indicating that they're converging to these random variables are very close to converging to a common distribution. And there's a red line going straight through the middle there, which is the distribution that is suggested by Miles's result. So if you pretend that it's a gamma distribution with mean 1 and this variance to mean ratio, you get a very good approximation. So what's going to happen is the grey ones, the values for n equals 1 to 25 are treated using the exact tabulated values, and the rest are treated using the asymptotic approximation. So you probably don't want to see this slide, but I'll put it in there and I'll circulate the slides so people can read it later. But basically what this means is that we will, for n equals 1 to 25, say we will use the tabulated distribution of an to approximate the contribution to the moment generating function. Then for values between 25 and let's say a couple of hundred, we'll use the approximation that comes from the gamma, the limiting gamma distribution, and then beyond that we'll pretend that it's 1 or trivial or something. And so when you do that, then you use all that stuff to compute the series expansion, approximate series expansion of this thing, and then you solve the equation to get the approximate intensity. So you can do this, for example, here is a command in the SPATSTAT software where we fitted an area interaction model. We asked what fitted parameters are, and then we just said, okay, do that approximation, and this is the result that comes out. And that takes a fraction of a second to do that, so that's the satisfying part. Performance of the approximation, so here you see the solid curve is the Poisson-saddlepoint approximation. The dots are the actual intensity estimated from simulation. It's a bit harder to do this for this particular model. Also, I'm taking a logarithmic scale here, so these are some of these values of eta extreme. A value bigger than 20 or less than 0.05 is a pretty extreme value of the parameter. This is a standardized parameter, so it's pretty unusual. But the approximation seems to be performing quite well, I would say, in different cases. So yeah, it seems to work. So in conclusion, this is a general strategy that is potentially applicable to any Gibbs point process model. But you need, as I said, you need to ransack the library looking for theorems to do the asymptotic part. So there's still some very interesting work to do with, these are basically a stochastic geometry problem. What is the limiting behavior of the canonical statistic, Tn, as n goes to infinity, for a particular model? In the case of this Widom-Rollinson or area interaction process, the approximation is quite good, I'd say. It also works, we've tried it for the saturation model developed by Charles Gaia. It's not quite as good in that case, but it still works for practical purposes. We can also extend it to non-stationary models. I just talked about stationary because otherwise we would be going cross-eyed. Okay, so at the moment there's a few papers which I guess would be best read if you get a copy of the slides later on, but I want to draw attention to the fact that Dominik Schumacher has written a couple of papers with Kaspar Stucki which are very relevant. And we have one which is describing this work, which is hopefully to be accepted by advanced in applied probability. And here are my contact details. So, thank you for your attention.